So let's start. Good morning, everyone. My name is Rishabh, and I'm working as a regional manager in Midas IT, and I'm looking after the entire north and east part of India. So before proceeding ahead, I would just like to do a quick sound check. If my voice is audible to you all, can you please drop a yes in the chat box? That's great. That's great. Great. So it seems I'm audible. So I welcome you all to the second series of this webinar, second session of this webinar series, which we are organizing on hydropower structures. So without further ado, I will like to request Mr. Chetan to give, a brief, uh, you can say a summary of what we had discussed yesterday and what we are going to discuss today. So just give me a second.
Hello, am I audible?
Yes, sir, you are audible.
Okay, can you see my screen? My screen is visible, Rishabh?
Yes, it is visible, sir.
Okay, so welcome you all to this session of the webinar. Uh, just quick recap of what we had done yesterday. So first, I had just a moment. So first we had these contours with us and we had dam access with us. We had used this e-text command yesterday to get the spot points of these contours, and then we had the rock line also from the borehole data. Uh, borehole test results at this site, and from e-text command we had taken the spot points to our Midas this Midas model. Then we had this what you call this hydraulic study done for this already hydraulic study done for this project. We had all the salient water levels and we had the spillway profile with us. So then from the spot points we had plotted this surface and this topographic surface. We deleted all the spot points to make our file lighter, and after that this is the topographic surface we modeled yesterday. After that we plotted the coordinates of the dam axis in our Midas window using the id command in AutoCAD, and taking those coordinates to the Midas window. So this was the dam axis we plotted yesterday, and there was a kink here. I mean, there is obliquity. I mean, this dam axis is oblique at one point. So that kink angle we had noted. Then we modeled one solid box here, okay, and placed it at a 0 0 location. This upstream face, okay, this that is the dam axis, that is at the dam axis. So so we had modeled these two solid blocks, okay, along the dam axis. Then we bifurcated these two solid blocks, okay. And after that we had plotted this rock line, and I mean, using the e-text command again, uh, I had modeled these points in the Midas, and then uh, this using this 3D polyline I had modeled this rock line, and then the rock bedding plane, and I had modeled using this translate sweep command, sweep translate command, okay. And so that rock bedding plane I had plotted on those two boxes, and from the this hydraulic studies, uh, we got to know that we need 27 overflow blocks to pass the flood. So so on conservative side, I mean, we had provided, I mean, I had modeled 30, I had considered 30 overflow blocks to be modeled. Okay, so then uh, the start location of overflow block I decided based on the, I mean, somewhat the lower elevation of the rock line. Okay, I mean, not rock line, this topographic surface and rock line, of course, also. And after that, so after that, I had plotted this spillway profile. Okay, so my sheet was developed in such a manner that these spillways profile uh, are plotted in the x direction. So I had to rotate these points in by 90 degrees here to take it to this to our dam blocks. Then I had plotted these spillway profile, flip bucket I had plotted, and I had imprinted all these geometries on the modeled boxes. Okay, and this after that, I had considered zero point 0.2 horizontal to 1 vertical slope on the upstream side. That line I had modeled. I had considered 10.5 meter this pier on the upstream side of this breast wall. So that line I had modeled. Okay, then then I had modeled this radial gate and Trunnion beams, considering 1.5 times the radius equivalent to 1.5 times the height of the gate. Okay, so these all these lines again I had plotted on this on the boxes which I had modeled. And then I had trimmed the upstream of the pier part. So and then I had modeled the thickness of the breast wall. I mean, this was just a preliminary dimensions. This may change after the analysis. Okay, just based on the past experience, 3 meters I had kept here and 3 meters at the bottom bulb location. Okay, so this then again these lines were imprinted on the box. Then the Trunnion beam I had modeled, and I had imprinted that. I cut this Trunnion beam at some 70 degrees, I think. Okay, then so that the operation of the Trunnion arms and this radial gate, that can be, I mean, smooth, and that there is no issue with the operation of these Trunnion arms and radial gates. So I had cut it at some angle, this Trunnion beam, and then I imprinted all the components: Trunnion beam, radial gate, I mean radial gate arc, this breast wall, then stop lock groove on the upstream side. Um, I hope all the attendees are aware of all these terms. They have been, I mean, analyzing dams. They are into hydrofield. If you are not, please just I mean give the just mention the questions in the chat box. I'll try to answer. Okay, but I'm expecting that whoever is attending this webinar, they are aware about the terms we use in hydropower structures. So yes, so after that, we had considered the top width of the pier from breast wall as 10 meters, so that the top road can be accommodated at the top of the dam. So that line I had imprinted. After that, to get I mean profile of the adjacent NOI block, I had plotted this 1 in 0.65 slope line of the adjacent NOI block. This may change actually. If from stability well calculations, if this slope is not stable, we will change it later on after stability. And after that, I modeled this profile of the pier. considering the maximum tailwater level on the downstream side, and I had considered freeboard, I think, of 4 meters above the maximum tailwater level. Based on the water levels, I had modeled this pier profile on the downstream side. Okay, this actually will be dependent on the water nappe based on what hydraulic model studies and based on hydraulic studies. But it seems to be reasonably high. So this true Indian beam location and the pier location. So, but anyways, it can only be finalized after the model studies. Uh, okay, and after that, I had uh, trimmed the upstream portion of the pier and filleted it with the 3.5 meter radius to get this pier thickness of 3.5 meter. Okay, and then I had mirrored it, and then uh, I had created this one overflow block, and then uh, translated this overflow block 29 times. That means 30 overflow blocks we had. So this we had done yesterday. Today I'll be modeling excavation for this. I'll be modeling topographic solid from the topographic surface we had modeled yesterday. So from that I'll convert that into solid. Then I'll be modeling excavation. We can get excavation volume, and then I'll be modeling the right side NOF concrete blocks and a part earthen dam profile also. So this I'll done, and today I hope I have prepared some captions also wherever some confusion is there. So maybe yesterday it was not there. So I hope today those captions will also be streaming along the video. So this is it from my side. Over to you, Rishabh, for this session.
Thank you so much, sir, for this detailed recap. And it is really amazing to see the intricacies which you are trying to maintain via this, basically in this session. So let us start ahead with today's agenda. And like sir has mentioned, today we'll be taking your questions. So if you have any questions which comes to your mind while during this webinar session, so please drop us in the chat box and we'll try to respond to your questions towards the end of this session. So before that, I just got to see one question that where we'll be getting the recordings. So like I mentioned in the webinar details itself, like once we are done with this webinar series, all the attendees will be will be shared an email in which the recordings of these sessions will be available. So just stay tuned with us. Don't forget to be here in the live webinar series. So let us start ahead with the presentation. I hope my screen is visible to all. Yes. Great. So this is our second session which we are going to cover in this webinar series. So like sir has mentioned, we are going to see the excavation modeling for the overflow block, modeling of right NOF block and a part of earthen dam. So without further ado, let's begin our session.
So welcome back to this session of the webinar. This is in continuation of the first webinar. So last time we modeled this OF block. Actually, this pier profile and whatever has to be provided by the hydraulic designer. And after the, of course, after the model studies, it needs to be freezed. But anyways, this tutorial is meant for modeling in Midas FENX for the analysis, even for the purpose of 3D CAD models. Okay. So, anyways, these sieges should extend in the mass concrete also. So, firstly, I'll do that. I'll change my work plane to these planes. Today, I'll be modeling NOF sections as well as uh, the earthen dam profile. I'll I'll I- I'll presume, I mean, clay core earthen dam. Okay, it can be some concrete core also. Uh, so first I'll translate this. I have to divide this solid. Okay, it looks fine. Can include this entire geometry. This overflow block geometry set. Next, I have these non-overflow blocks also with me. Okay. Just switch it on this side. Okay. Then I'll extrude it. Okay. Upstream slope I had kept 0.2, horizontal is to 1. I'll change my work plane to this plane first. Extrude this, say normal 35 meters, some arbitrary large distance. Okay. Then I can divide it, this slope. Okay. So bottommost foundation level is this. While modeling the excavation, I'll reduce the height of NOI block. Okay, so firstly I'll change my work plane to this level, 213 level. Okay, I'll create one surface here. Divide this. Okay. Now I'll plot FRL here. FRL is 5 meter below the top of the dam level. Translate this curve. We have 5 meters. Okay, I'll imprint this delete this line. Okay. And extract this. Say downstream slope, I presumed say 0.65:1. After stability, if it doesn't work, we'll change the slope. But initially, we'll keep say 0.65 horizontal to 1 slope. Extract this, rotate this. .65:1. Is that? So I'll Boolean fuse this one and this solid. Okay. Divide this. This curve. Okay. And suppose top width of the road here is say 8 meters. Okay. Change my work plane. Okay. And I don't need this. So this will be the profile of an a block. Okay, presumed. Okay. Probably NPR I can have the additional this profile also, but let's keep it as it is. Okay, can do it later on. Then let's start creating excavation now. For excavation, I'll presume that in rock, cut slope is 1:4. Every 10-meter height, there is a bench of say 3 meters. Okay. For excavation, I'll require 2 points. 1 point here, and the point here on the extreme corners. Okay. And I have created one sheet for this as per the slopes. Let's see. Just switch it off first. This overflow block also. Okay. So this is the rock line. Okay. So this elevation is approximately 225. Look here. 225. Okay. So up to 225, I'll consider 1 in 4 slope. And beyond that, temporary slope of 1.5 horizontal to 1 vertical. Okay, so this I'll consider. Okay. Okay, so I have these 2 points. So I need the coordinates of these 2 points first. So I'll just copy the coordinates of these points. Copy, paste it here somewhere. Okay. So it's already, yeah, this is fine. Already I have done this before. So this one, properties, copy, paste it here. So you can develop this sheet. This is not a tough one. See, you have to practice. I'll be using this wedge feature of in Midas FENX. You have to practice this. What I mean parameters it is asking, software is asking. Okay, just have a look at this video. It's not that tough. These are, this is okay. This is not fine. Y is minus 3900.86. Okay, this is now fine. Okay, so 213, let's keep it up to here. Let's keep as it is. Beyond this, let me change horizontal slope to 1.5, and probably in y direction, other direction, let's keep it say 1 or maybe 0.5 horizontal. Okay, here let's, okay, all other slopes let's keep. So these are all the parameters required to input to use this feature wedge. So okay, let's start creating this wedge. I don't need these points anymore. I'll delete this. Okay, just switch it off, change it to XY plane, wedge. Okay, copy, paste it here, copy this, paste it here. This is 10, this is 93.37 here, dz x min minus 2.5 and 463. 463, this one, this much, and finally how much? 100.0367. Okay, let's see. Okay, so this will be our excavation bench. Let's create the other one. Okay, I should have applied it instead of putting it off this wedge dialog box. Anyways, I'll do it again. Apply. Okay, next, run. V, 132.0637. Okay, apply. Okay, next. V. This is fine. Control V. Fine. T, and this is 198. Apply. Okay, let's see. Have we crossed this? No, actually, issue is that whatever I'm doing it in Y. I mean, towards the Y. So actually, in Midas wedge we create, it's in this Y direction. Probably Midas will look into it and probably come up with some other tool where we can create this wedge in vertical direction also. I'll rotate this later on. I'll rotate this now. Okay, let's see. Let's finish this. Okay, and now I can rotate this. Firstly, I'll boolean this. Boolean merge all these faces. Okay, and now I can rotate this. '90 degrees. Okay, now I can see. So I've crossed this NSL. So this was my rock line. Okay, so it's fine. And probably what I can do, I can extract faces from here. Extract face, and I can remove the top and bottom faces like this. Okay, okay. Then probably I can rename it to what you call excavation. Okay, this is that. So I can boolean this also. I think I need this also. Extract. Okay, I can boolean these faces also. Boolean all these faces to create one. Okay, now I'll create excavated profile from this. For that, I'll I'll change my work plane to XY plane. Create a face here within this boundary. Okay, for that, firstly I'll unselect all and start creating my face from here. Now I can select required points, point snap and snap, perpendicular snap. Okay, the middle snap also. So this is it. And to extrude this, mm, 293 is the dam top now. Say extrude it to say 300 meters, some arbitrary large distance so that it crosses this work plane. I mean this NSL. Then I can divide this. Delete this. So this is the actual NSL. Now don't need this wedge, this. Okay, probably I can extrude it a bit in this direction, extrude this. Okay, some 100-200 meters in this direction, say 500 meters. Okay, and boolean these, presuming that NSL river is flatter here, and it is flatter here as per the contours. So I'll presume that my NSL will be somewhat like this, and now I'll divide this by these curves without deleting them. Okay, so this will be my excavated volume. Let's see how much is the volume. So this will be the excavation volume. Okay, and if I hide this, I'll get the excavation. This will be my excavation profile, somewhat like this. Okay, oh sorry, wedge, hide it. Actually, I should have moved this translate. No, it is correct. Okay. Divide. This is the excavation volume. The volume is this much. Okay, bit less. It should be actually this one. And okay, delete it. Okay. So probably this center block I can terminate at some distance. Let's see. Where I can terminate this. Let's make it transparent. Somewhere here probably. Okay, some X direction. How much? Keep something here. Say here it is 13,000, 13,100. Somewhere. Where is NSL? NSL also I'll sell somewhere up to here. No, I can keep my what you call earthen dam. Okay, from here slope is getting one approximately 150, 160 meters. Okay, I'll have 8 blocks of NF section. With 20 meter, each having length of 20 meters. And beyond this, I'll have earthen dam profile. Okay, so this was the rock profile. You can translate this. Okay, I can divide this. As per the rock line. Okay, probably here I'll take some liberty that I'll have vertical slope in this direction. Okay, just a temporary slope, small, very small, to 3-4 meter high maybe bench would be required. So what I'll do, I'll boolean cut this from here. Okay, so this will be, I'll be modeling the, left bank later on. So this is right bank, and afterwards I can have earthen dam profile here. No, before earthen dam, I think I should do another thing also. Actually, this may not be acceptable. This seems to be at one plane. Okay, keep it at 225 level, and probably I'll extrude this direction by at least say 5 meters. Okay, and from here I can have this sort of slope. Okay, probably this sort of profile will be acceptable, at least 5 meter straight portion, then curved one. Okay, and similarly here. Okay, here also extrude. 5 meter like this. Then we can have, okay, where's these two? This should be fine, and they can have, what is this level? This is 225.581. Okay, I'll keep everything at this level. Should it be acceptable? Can Boolean cut this? Okay, so probably resume that, but it can be cut vertical. Okay, these are temporary slopes. Okay, move forward. Renaming it so that it's easier to work. Another another set. Okay, now I'll start modeling the earthen dam profile here. Okay, create a box, a large box here. There's some 1100, 1000 meter, 1100, whatever. Width say 200 meters, height say 213 to 293, say 100 meters. Okay, extract face, translate this face. Ten meters. Divide this. No, say I'll have benches at say 15 meters will be fine. Okay, I'll keep earthen dam slope as 1 in 2.5. 1 in 2.5. So 15 meter into 2.5 is 37.5. Okay, divide this first. I'll have 5 meter bench. Okay, let's hide this first. Use this chamfer tab, chamfer it. Okay, chamfer this direction 37.5. This direction 15 meters. Okay, so this is 1 in 2.5 slope. Then extrude this and say 5 meter bench is there. 5 meter bench. Okay, extract this. Extract this. Okay, Boolean fuse these two surfaces. Okay, translate, copy 2 points. 5, 6, say 5, 6. Okay, whatever. Okay, I can extrude this further. Okay. Divide this solid by, okay. It happens sometime, no issues. Then probably extrude these faces. Vertical direction by some arbitrary large distance. I'll subtract this. I don't need this face anymore. Okay. Okay. Will be sufficient. Let's see. It should be sufficient. Okay. And okay. Slate. This is 8 meters. Cut this. Okay. Mirror it. And extrude this. Okay. So we have 8 meter wide road here, and this is the outer shell of that. Now we have to, suppose this is a clay core dam, we have to create a clay core here. For that, what I'll do, a furrow is FRL and MWL is 5 meter below this. So I'll extract this face, translate this face, minus 5 meters. Okay. And suppose clay core slope is 1:1 this side and 1:1 this side. Extract this. Rotate. .45. Okay. Here. Okay. And mirror it. Okay. Let's try to divide this. These three surfaces. Let's see if it works. Sometime it doesn't work. Then I'll have to apply some other method. No, it's not working. Okay. No issues. Translate this. Yeah. Let's try to divide now. It's divided. And similarly, this. Okay. Just hide these ones. Change work plane to this plane. Okay. Okay. So this will be the clay core. Pulley on these. This outer core. The dam. And this will be the clay core. Okay. Now probably we'll need filters also here. Upstream and downstream filter. Let's say 1.5 meter is the thickness of the filter. It all depends on the gradation.
the variation of size between the clay and the outer core. That I'll do 1.5 meter. This side also say okay. Okay, we can boolean cut this, this, this without deleting the tool. Okay, now we have this filters. Okay, we'll have a horizontal filter on the downstream side, but first we have to match it with the natural ground level first, and then we'll have clay core extended to the rock level. That also will do. And on upstream side we will require some riprap arrangement also. That also we will provide. Okay, let's create riprap first. For that, extrude this face. Say 600 mm riprap is there. Normal direction. Much say 0.6. Okay. The second boolean. The second boolean. Why? Okay. The second boolean. This. sometimes these small things takes a lot of time. I'm sure you will find some easier way to do this. So we have created this web. Okay, this I don't need these things. Okay, I can now boolean cut this. I have 600 mm riprap here and this one. Okay, then probably okay, we have to terminate this earthen dam somewhere within the concrete block. So for that, what I'll do, change my work plane to the center point. This face and divide this entire solid, all these solids, this face. Okay, and then can revolve this, rotate this curve. Should be revolved, sorry. Okay, similarly here. Okay, here this NI block. So it will terminate here and I have to cut this entire block. Okay, that I think I'll take up in the next session. Next session, I'll take this what you call clay core up to the rock. This shell I'll eliminate at the surface level, and I'll have a horizontal filter on the downstream side here, depending on the topographic surface. And then here I'll terminate these as per the topography and as per this NI block and OI block. That I'll do the next session. Thank you for this session.
Yes, so that was again a very detailed presentation. So now we will answer a few of the questions which our attendees are asking. So I'll just request Chetan sir to please answer few of the questions which our users are asking.
Am I audible, Rishabh?
Yes, sir, you're
Hello,
audible.
Rishabh. Yeah, I can't see questions here. Okay, just what do I do to see the questions? Where are the questions?
Uh, so you could find it in the questions tab.
Can you see
Are
my
you able
screen?
to?
Where is that?
Or is it possible? Can we just read out the questions one by one, sir?
Yes, that would be fine. Yeah.
Great. So we have received this question. Mr. Bharat is asking, good morning,
Yeah.
this is Bharat. So do we need to
Yeah.
model all the dam blocks in a single model and analyze them, or can we analyze each block separately?
Well, these first four tutorials are meant for modeling only. Actually, in analysis, we don't model entire dam. Analysis is carried out for each block separately. See, but modeling entire dam will help in better mitigation of interface issues between the dam blocks and ground initially, and reduce the drafting time and review by the engineers also. You can cut sections, plans in midas and have a view of that. You would notice it doesn't take much time to model in midas. Uh, See, 1.5 hours it took to model a topographic surface and entire OA block in the first session. Okay, and entire this entire modeling session, first four sessions, that will take about 5.5 hours. I don't think you will mind. I mean, spending 5.5 hours to get a complete 3D visualization of your entire project. So it's always good. I mean, the first four webinars are for modeling only. So in next, you will find from fifth webinar onwards, I'll be analyzing one block only. So for analysis, it's not required.
That's great. So I hope we have addressed your question, Mr. Bharat. Now, sir, there is one more question. Can we use 3D tools to produce the model and apply loadings in Midas?
3D. I'll be applying loadings. Just wait for webinar fifth. In webinar fifth, sixth, seventh, eighth, I'll be applying loadings, analyzing it. I'll be analyzing it for dynamic ground motion, time history also. Just wait for webinar fifth. 5, 6, 7, 8 are for application of loading, analysis, all that stuff. Yes, it can be done, of course.
Great. So we have one more question. How do the individual dam block analysis and full dam model analysis differ, and which approach is preferable?
Well, see, normally dam blocks are analyzed for the forces from upstream to downstream side on the adjacent side in a cross valley direction. So the dam blocks are confined between the inner blocks and maybe rock or what. So stability is not a criteria in a cross flow direction. Stresses can be. For stress analysis, we can consider the adjacent blocks. For stability, the upstream to downstream forces, those are critical. We should check stability along the flow along the flow forces of the dam, and stresses, it we may, I mean, sometimes have to model the adjacent blocks also. Say with CJ, we can take the contribution of the for say OA block, we can take the contribution of the uh, adjacent block peer. Okay, that will, of course, I mean, that will restrict the movement of your block, the adjacent block. Okay, so for stress analysis, we can consider the contribution, but again, it's your engineering acumen up to what extent you should model your dam blocks for the analysis. So as I said that for these first four tutorials are for modeling only. For analysis, of course, then we will see, I mean, how much we should model, what model we can extract from this entire model for the analysis. Okay, so it all depends on the type of analysis what you are doing. For stability, it's not required. For stress analysis, sometimes it may require.
That's right. Thank you so much for your detailed answer, sir. Now, I'll just discuss one more question and then we'll wind up this session because it's already about 12:30, sir. And we'll have just a couple of more questions which we can address via emails. So don't worry,
Yeah.
engineers, we will address each and every question of yours. So just one last question. So is it possible for one to import a model from Civil 3D to Midas from modeling perspective?
I think this you can better answer. Civil 3D DW DXF, I think you can import, but it's always better to model it in Midas only. Midas has very good CAD tools, I mean inbuilt CAD tools, so you will have more confidence on accuracy of the model. So it doesn't take, if you are, I mean, if you have practiced these tools, it doesn't take much time for modeling in Midas only.
That's nice. So I can see some responses as well. Like people are actually giving their opinions and people are actually participating. It's great to see. And thank you so much, sir, for this session and for your time for addressing the queries. Let's meet tomorrow, everyone, for our next session, which we'll be continuing the modeling part of the dam. So I believe this is it. Thank you so much, everyone. Thank you so much, Chetan, sir. Thank you so much for your time.
Thank you.
And
Thank
let's
you.
meet
Thank you.
tomorrow at the same time, 11 a.m. Yeah. Thank you.
Thank you.
Have a great day, everyone ahead.